This is the screencast for section 2.3, example 2. We're going to start out here with introducing this theorem. A polynomial function of degree n has at most n minus 1, so one less, local extrema, and at most exactly that number zeros. So for example, a polynomial function of degree, let's go with 5, has at most then 4 extrema and at most 5 zeros. And we're going to take a look at a couple examples that will demonstrate that. You could also play around with some drawings of a 5th degree, 6th degree polynomial, etc. And you can see how this theorem does hold true. So example 2 says graph the polynomial function, locate its extremas and zeros, and explain how it is related to the monomials from which it is built. Oh, don't we love explaining things in math? So first, let's graph this polynomial function. Oh look, there it is. This function is always increasing. It doesn't change from increasing to decreasing, so it has no extrema. It has a 0. Let's see, it has a 0 at, well, 0, 0, the origin. Then it says explain how it's related to the monomials from which it is built. Well, I need to look at those monomials individually. So in the y equals, in y2, I put the first monomial, x cubed. Now let's see what those graphs look like together. Very close to the same, especially on the outside. See how it gets dark? They get very close to each other on the outside. Now let's see what happens if I turn off x3, x cubed, and turn on y3. There's the original. See now towards the inside, let's hit zoom 4 on that. The inside of this function looks very much like y equals x. So I'm going to say in my explanation, the ends of f of x look like y equals x cubed. The middle towards the y-axis looks like y equals x. Part B asks the same thing about x cubed minus x. So I put that and then into my y1, and then I also found the maximum minimum. We've done that several times before, so I wouldn't show you that in the screencast. It also asks us to find the zeros. Now these zeros are a little bit more complicated, so I am going to use my calculator to find them. I know there's a 0 at 0, 0, but I'm going to find the other zeros. So second calc number 2 is 0. Now this asks me for a left bound, so since I'm looking for the 0 right here at what looks to be about x equals 1, I'm going to go to the left of it, hit enter, go to the right of it, hit enter, and then go back in the middle and hit enter. And I do get that there is a 0 at 1, 0. Then as you may have predicted, the other one will land at -1. Second calc 0. It's asking me for a left bound, so I need to go to the left by hitting the left key of the 0. Enter. Now the right bound, I'm going to go to the right of the 0, hit enter, and then I'm going to guess, so I'm going to get as close to that 0 as I possibly can. And there is a 0 at -1, 0. You should also be able to figure that out algebraically. You can take x out of the parentheses, which leaves you, or excuse me, you can factor out an x, the greatest common factor, which leaves you with x squared minus 1, which then is x times x minus 1 times x plus 1, giving you your 3 zeros at 0, +1, and -1. So the zeros are x equals 0, well, 0, 0, 1, 0, and -1, 0. Then it wants us to explain how this function is related to the monomials from which it is built. So again, I'm going to look at y equals, and I'm going to put x cubed into y2 and see what that looks like. looks like it's getting pretty close to looking like this. I'm going to go zoom 6 so I can see out. Yeah, look at that. It's getting really close. On the outsides of the function, it's taking on the x cubed shape. Then I'm going to predict the same thing probably with part A. The other term, though, is negative x, so I have to put in a negative sign and hit graph. And I want to see closer in on this one, so I'm going to zoom 4. And yep, again, the inside of the function is taking on the shape of the second graph, the second monomial. So I can pretty much copy the same statement. The ends of f of x look like y equals x cubed, but the middle towards the y-axis looks like y equals negative x this time. Now I want to point out here that theorem that we talked at the beginning of the example, a polynomial function of degree n, so like this is degree 3, has at most n minus 1 local extrema. So in our example B over here, we found out that at most it has 2 extrema, the degree minus 1. It also has at most 3 zeros. So there are 3 zeros here in example B. But in example A, there's only 1 zero, not 3. And there aren't any extrema. So again, at most, a polynomial has n minus 1 local extrema and at most n zeros. The now try problem number 7 asks us to graph the polynomial function negative x to the 4th plus 2x, locate its extrema and zeros, and explain how it's related to the monomial functions from which it is built. So, I have the graph, which kind of looks like an upside down parabola, but this little weird lopsided part right there. So now I'm going to locate its extrema. There's definitely a maximum right there. So second calc max. So there's an absolute maximum at 0.79, 1.19. Now the big question is, what are the zeros? So I am going to factor out an x, and I'm going to leave on the inside negative x cubed plus 2. So either x equals 0, so the origin is one of the zeros. The other one, negative x cubed plus 2, could equal 0, so subtract 2 from both sides. X cubed equals negative 2, negative x cubed equals negative 2. Divide both sides by negative 1. I get x equals, actually, if I take the cube root of both sides, I get x equals the cube root of 2. That doesn't need to be read. So now, if x is the cube root of 2, that's this little value right there. So my zeros are 0, 0, and 0, comma, the cube root of 2. So I graphed the polynomial function, I located the extrema, it's an absolute max, I found the 2 zeros, and now I need to explain how it's related to the monomials from which it is built. So, that part. In y2, I put the first term, negative x to the 4th. Now let's see how that compares to the graph. Surprise, surprise, just like the example, parts A and B, the outsides of the function, the ends of the function, look like that first term. Then let's go into y3 and see what happens to the 2x part. I'm going to hit zoom 4 so I can see the middle, predicting that the middle is going to look very much like that. And there it is. The middle looks exactly like that. So once again, the first term describes how the ends of the function look, and the second term, 2x, determines how the middle of f of x looks.